topic 2.2, forces. So the essential idea is that to calculate classical motions on the Earth, we know that there is a force required to change any motion. And so let's get into it. Forces are a push or a pull exerted on an object. And so do objects have to be touching in order for forces to happen? No. Think about magnets, right? So sometimes forces happen from what we call a distance. Although we best identify forces as like through physical pushes and pulls, forces can happen when there is no contact between two objects. We will study 4 non-contact forces this year: gravity, electrical force, magnetic force, and nuclear forces. Forces will speed things up, slow things down, cause things to accelerate. Wait, haven't we seen that list before? Oh, that's what acceleration is. So forces cause accelerations or changes in motion. So Newton was the one who came up with all of these ideas about forces back in 1729. He studied a lot of motions and he came up with 4 kind of laws about what's going on. And here they are in kind of pictorial form, but we're going to talk about each of them individually. The first one, let's start with, is his law of universal gravitation. So Newton is obviously famous for gravity because it was kind of this weird, way to see the world that no one had really thought of. It made a lot of sense, but it kind of no one had put it down into words. And so he came up with the idea that the pull of gravity between two objects, say like the moon and the earth, was the same as the pull between two objects like an apple and the ground. And so he came up with the idea that gravity is universal. It's happening everywhere in the same way. And actually, he did a lot of calculations and data using this equation to back it up. So let's talk about this equation. Fg equals g times m1 times m2 over r squared. Fg is the force of gravity, represented in newtons, in honor of Isaac Newton, and it's equal to g, the gravitational constant. This is in your data booklet. It is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. It's a measured value that scientists have agreed upon over the years. M1, whatever mass you're talking about, the first mass, because this is an interaction between two objects, usually massive objects, but it happens to everything. And M2, mass 2, both measured in kilograms, and this is divided by r squared. But r is the distance between the center of masses. Although r we typically think of in math as being a radius, it's actually the distance between two objects. Why did they represent that with an r? Well, because usually we're talking about the gravity from a planet. And since the center of the mass of the planet is the center of the planet, you end up with the radius of a planet. So I think r just made sense to them. But so it's the distance between the centers of the two objects. And so newtons, this is a new unit. It is kilograms meters per second squared. So it is a derived unit. It comes from an equation, and we'll get into the equation in a bit. Side note, I said the center of masses. When we think about mass, objects have what we call a center of mass, the spot where if you directed your force, you would get a maximum effort. So for example, if I have book, right? If I tug on the corner, it doesn't do much. But if I tug on the middle, it does a lot. And so the center is where you want to be dealing with. Objects obviously have different densities, different actual uniform objects, but we're going to assume things are uniform in this class. So even if you have something non-uniform like a cup, the center is where we're going to assume the mass is. So you're measuring the distance between the center of the two objects, or the center of mass. Now, in advanced versions of calculus-based physics and college physics, you'll actually find the center of masses. There are equations for this, depending on density and other things. Why is it called universal gravitation? Again, that means it works everywhere and between any two objects. So this formula led a lot of credibility to the heliocentric model and Newton actually got this idea from Johannes Kepler, who was the one studying the planets, who came up with a lot of the heliocentric model. And so he got this data and all the information from him. So don't forget, scientists, even the greatest scientists, use science knowledge from other people. And so on Earth, We know after careful studying that the mass of Earth is 5.97 times 10 to the 24 kilograms, and we know that the radius of Earth is 6.37 times 10 to the 6 meters. So using the gravitational constant, which is in your data booklet, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, what would be the force on like any object on Earth, like a random cup? Well, that means we don't know whatever M2 is. We're just generalizing. But we can plug in M Earth for M1, G for G, and radius of Earth, because this is pretty much on the Earth. Yeah, there's probably like a meter above the ground. But if we're talking about 10 to the 6 meters, does that matter? No. So let's plug these numbers in. Do it. Pause. Do it. You're actually going to find that the force of gravity is negative 9.81 newtons per kilogram times a mass, so 9.81, wait, that's the acceleration due to gravity. That is the actual pull from gravity on any random object on Earth. Weird. So that was obviously why we call it the acceleration due to gravity, and it's how we found out the acceleration due to gravity. And so Newton had 3 other laws of motion that he wrote down to describe how all objects behave. You've probably heard them before. They are: 1, an object at rest will stay at rest, and an object in motion will stay in motion in the absence of an unbalanced force. 2, unbalanced forces accelerate objects. And 3, all forces have equal and opposite reaction forces. So, obviously, the first one came from a lot of careful studying and looking at objects and saying, okay, if I don't do anything to this object, it'll stay the way it is. That's the easy part, the first half. The second part was a little hard, and people had issues with it. An object that is in motion will stay in motion unless there's some unbalanced force there. What about something that I kick across the floor? A soccer ball, if I kick it across the floor, it comes to a stop eventually. Well, again, people didn't have amazing telescopes, and they didn't understand that there's actually something happening between the ball and the floor that's unbalancing it. It's there is some sort of a force there, and we'll get into it a little bit later in here, but there is some sort of a force that stops most things that you're probably actually familiar with if you've done any studying in science. So 2, any unbalanced force will cause an acceleration or a change in motion for an object. Now, there is more details to this, and I'll get into it in a second. And then the last one, all forces have equal but opposite directional reactional forces. So, for example, when I push on the table, I can feel the table pushing back. There's some sort of a reaction by the surface because it doesn't want me to go through it. Now, a table has a lot of reactive force. A piece of paper wouldn't. And so I would break through the piece of paper. But there would be some sort of a reaction that the surface gave me. And so this reactional force will be equal, but in an opposite direction. So like pushing up, if I'm pushing down, to my push down. And so this is actually what allows us to even move. So as we step on a floor, the floor pushes on us so that we can actually move forward. So in kind of mathy form, law 2 is this equation. FUN, or force unbalanced, is the mass multiplied by the acceleration. Law 3 is the force from A to B is equal but opposite in direction to the force from B to A. Again, you don't need to necessarily know those, but you've probably seen them before. One does not have a mathematical equation because, it's just kind of a thought process, and there's no actually thing you would calculate about it. It's what sometimes is referred to as inertia, the fact that an object in motion stays in motion and the object at rest stays at rest. So let's get into law number 2. The force net is equal to ma. So the way Isaac Newton actually wrote it, he said that the acceleration of an object is directly proportional or equal to the net external force acting on the object and is inversely proportional to the object's mass. So that's a math equation. And if you rewrote it, it's A equals F over M. And so that is this equation. We just typically use it to calculate force. So F equals MA. Now, a net external force. Why did I have to specify that? Well, think about it like this. If you're in a boat, you could be pushing left and right on objects, but it's not going to change what's happening to the boat. Just like how, as I'm sitting here, my heart is pumping blood through my body, but it's not pushing me left or right or up and down. It's just doing some sort of a force inside the object. Now, if all of a sudden someone were to come and push me, I would, of course, move because that's something outside of my system. And so we're going to spend a lot of time figuring out, well, what's inside the system and what's outside or external to the object. And so net also is an important thing. So since only the forces acting outside of it can affect it, it's actually only the sum of all of those things added up in their directions that you need to worry about. It's the net amount. So when we talk about a net value in mathematics, we're talking about adding up positives and negatives and getting some final amount. So for example, in this picture, in the vertical direction, you have 600 kilonewtons going up. And so we typically talk about up being positive and down being negative. So if we have positive 600 kilonewtons, but the weight is 600 kilonewtons, so we have negative 600 kilonewtons. 600 plus negative 600 is 0. So we don't have to worry about forces up and down. This plane will not be accelerating up and down. But left and right, let's call left negative. So we have air resistance, which is a negative 200 kilonewtons, and we have engine thrust, which is 500 kilonewtons, positive. So negative 200 plus 500 is 300. So we have 300 kilonewtons to the right. This guy's going to start accelerating to the right, or its velocity is, since it's already going to the right, is going to increase. All right, so let's try it. Pause it, do it yourself. Okay, you're back. So you should have gotten a value of, so let's assign left as negative. So negative 8 plus 12 plus 6, you're going to total of 14 to the right. I think I did that math right. No, 10. 10 to the right. So that is this one. Try it again. Okay, so you should be back after pausing. So we have 11 going upwards and 12 going downwards. And so again, if you do the traditional up is positive, down is negative, you have a total of negative 1 newtons or 1 newtons downward. You could always use the word downward instead of a positive negative if you're not sure what you want to do for positive and negative. There are many types of forces, and here are the ones listed in the books, but there are also many different names for the same exact force. And so I will try and be consistent, but I don't really like the books version that they use. So you may hear me accidentally call it something else, and I will just ask if you're confused. So the ones in your textbook are weight. I don't like to call it weight because it doesn't help you remember how to calculate it. I like to call it the force of gravity. So you're going to often hear me call the force of gravity your weight because it's how much you're getting pulled down by gravity. Tension force or compression is, so tension force is usually in like a rope or some sort of a stretchy force, stretchy object. So like if you were to stretch something, you get some sort of a pulling back of the material. It's called tension. Compression is when you push on a material and it kind of indents. So if you think about that compression, that push in, it's very easy to kind of see with like a stress ball. You can see it kind of pushing in. It's a compression of the actual physical material. And so forces can actually change the material shape. Reaction forces, we already kind of talked about. There's always one that sort of is normally there. So we call it the force normal, but we also call it that because it's perpendicular to a surface. So whenever I push on a surface, the surface pushes back on my hand, perpendicular to the actual surface area. And so if you've been in math for a long time, you know another word for perpendicular is normal or orthogonal. And so we call this the force normal very often in physics. You will hear it called that, but it is a reaction force from a surface. Friction and air resistance are other very common forces that we're going to talk about. You may also hear it called drag, especially when it's a fluid like air or water. Upthrust is one of those weird ones that the book calls upthrust, but we usually think about upthrust only kind of when you're in a fluid. So like say a boat in water, the water kind of is pushing up on it. So it's thrusting it upward. So upthrust. And if you've studied a lot of kind of chemistry and stuff, this is actually also called buoyancy. So this is a force buoyant, sometimes called that too. And then we already talked about the other non-contact forces. We'll talk about electricity, magnetism, and nuclear forces. So something important to know about forces, since we talked about the net forces and balancing and adding all the different directional forces, if an object is in trans-equilibrium, that means there is no resultant force when you add up all the forces. So for example, in the first picture down here, 50 newtons to the left, 30 newtons to the right, this is not translational equilibrium. Now I didn't give any numbers on the other ones, but say this ball is sitting still. The weight of gravity pushing into the ground will be balanced by the ground pushing up to it. And so whatever the weight is going to be negative, like let's say it's negative 200 newtons. The ground reaction force will be positive 200 newtons, and you'll get zero kind of force. And that's because we can visibly see that the object is at rest. And so according to Newton's first law, it will stay that way since there is no external force. Now, if someone comes to kick it, that's a different story. Now, that's only half of Newton's law, though. An object at rest will stay at rest. If an object is in motion and it will stay in that particular motion, you could also have balanced forces. So let's look at this airplane. So it says it's balanced, which means that the force of the lift is equal to the force of the weight. We already saw that in another example. But in this case, the thrust of the engines is equal to the amount of air resistance or the drag going backwards. And so that kind of equaling out means there will be no acceleration. F equals ma. There is no acceleration if there's no force, no external force. And so although it is in the air, it's still moving at some speed. There won't be any change in that speed, or this will be a constant speed, which is super great. So say it's moving at 30 meters per second, you're going to keep having 30 meters per second. It's a uniform acceleration of 0. So how to calculate the common forces around us? Well, so again, weight, I like to call force gravity. So F with the subscript of G, because it's equal to your mass multiplied by the acceleration due to gravity. And so sometimes this will be a capital W for weight, but I like to call all forces F and then just subscript them. So you can call this force W, you can call this force G, whatever you want, but it's the mass multiplied by the acceleration due to gravity. A normal reaction force is always just opposite whatever is opposite it. So I said that the force from the table is equal to the amount of weight pushing into the table. But if I were to lean against a wall, the amount of reaction force would be the amount of kind of force I'm actually applying to the wall, which if I'm leaning is going to be part of my weight. And we have to use the angles and stuff to figure it out. The last part, the one that you're going to usually calculate, is force of friction. And there is an equation for it, and I'll dig into that equation a little bit later. You might see it represented this way, but your data booklet represents it differently. But I'll get into that later. So let's do an example. So say you have two identical blocks. They're both of mass 50 kilograms. One's on the ground and one is on a ramp, but both are not moving. They're in translational equilibrium. So we want to find the value of the forces. So for example, why did they have to tell you that the mass is 50 kilograms? Well, to calculate the weight, W or Fg, we need to know the mass, which is 50. And then we use the acceleration due to gravity, negative 9.81 meters per second squared, to calculate the weight. So both of these weight vectors will be 490.5 newtons. And so in this case, it's super easy to find the other force because according to Newton, if it's in translational equilibrium, or it's acting according to the first law, there's no net force, or so the forces add up to 0. So if this is negative 490.5 newtons, this is positive 490.5 newtons. So this is the normal reactive force, or the force normal, capital N. Now, on a ramp, it's a little bit not So easy. Because although the weight straight down is 490.5, well, part of that is pushing into the ramp and part of that is trying to pull the block down the ramp. And so you can see that the force of friction is balancing the pull down the block, and the force normal is balancing the part pushing into the ramp. And so this is one of those cases where actually setting up your coordinate system on the ramp, X being up the ramp positive and down the ramp negative, and Y being up off the ramp positive and down into the ramp negative, will help you out. Because in order to balance out these forces, I actually have to find the components of one of them or multiple of them so that they're in opposite directions. Because according to Newton's third law, only objects that are in opposite directions can be equal and opposite. So if you set up your coordinate system on the ramp, all you have to do is split the weight force into kind of down the ramp and into the ramp. And so let's do it. So if I were to imaginarily draw in my little weight vertical and weight horizontal, this becomes the angle of the ramp. You can kind of check using geometry and drawing in parallel lines where that actually happens. And so if this is the angle, my part that's balancing friction will be 490, or the weight force, times the sine of the angle, and my part that's balancing the normal will be the weight times the cosine of the angle. And so again, we practiced this last week, so hopefully it's not too stressful on you, maybe finding where the angle is, but other than that, it should be okay. And so the last thing we need to talk about is that force of friction. And so this is a resistance that happens due to microscopic collisions between two surfaces. And I know I cut that off with the picture, but I wanted to find a good picture. So no matter how smooth you think a surface is, if you could get a microscope out and zoom in to the atomic level, there would be some kind of gaps and uneven jaggedness to the material. And so when you have two surfaces that are actually touching, you're going to get what we call static friction or dynamic friction. It depends on if the object is already moving or if it's been sitting there for a while. So static friction is the amount of force it would take to get the object started moving. And so I like to think about this as if like this blue surface had been sitting there for a long time. Force of gravity would push it downwards and all of the little peaks would fall into the valleys until it was nice and nestled in and they were kind of almost glued. And so when I have to start to move this object, I have to push it until it goes up the little peaks. And so I have to give it a little extra. Versus dynamic friction is the amount of force that will come by just random collisions of the peaks as they're brushing past each other. And the faster I go, actually, the less this might be an issue. But there's a kind of a maximum amount that I will get when the peaks are hitting each other because I can't get the surfaces to not touch due to that weight force. And so the way we find the force of friction is using these two equations in your data booklet. Force F is less than or equal to mu S times R. And so what are these things? So obviously FF is the force of friction. And mu is what we call the coefficient of friction. And it's something that you have to measure on a surface. And there are some typical measurements like paper against the table or metal on metal that scientists have made over the years. And so it's some sort of a ratio between the force and something called the reactive force or the normal reaction force, the kind of amount of force pushing into the surface. So this is usually going to be some component of your weight, so your force normal. And so I like to write this usually out not with an R, but an F subscript N because it's the normal force. You may see me do that, and I will apologize because this is how it's in your data booklet. And so either you're going to have the force of friction, which depending on how hard you're pushing will just match until, of course, you overcome it sitting down into all those peaks and valleys. And so that's why it's less than or equal to, because if you barely push on an object, friction doesn't have to resist you much. You won't get a lot of sideways pushing between those peaks. But Force of friction dynamic will always be equal to, because it's going to be the amount that is the ratio between how much is pulling backwards and how much is pushing in. And so we'll do actually a lab where we calculate coefficients of friction so you get a sense of where this comes from, and kind of what's the difference between static and dynamic. So hopefully this introduction to forces makes sense. But please go read your textbook, because there's more details in there that I just can't cover in a lecture. So please go and read that. And hopefully if you have any questions, just let me know, and hopefully you'll get there.